Hello everyone, welcome back to ECE410 Power Electronics, class number 3. In class 2, we talked about impurities into the component. Class 2, we had an inductor which had the series R into it. So how to deal with that inductor with R, L in that. So after that, we're gonna introduce one more impurity here. In this time, we have a capacitor what has a series resistance of RC right here. So if you have that, how do you handle that one? So last time we had an L with series RL, we did the balance of energy across that inductor. This time we're gonna use the energy balance across the capacitor here. So if you look at here, your switch 1 is on. When switch 1 is on, you know this complementary switching, that means 1 is on, 2 is off, and vice versa. When 1 is on, you're getting inductor getting energy from the source. In the meantime, your capacitor is supplying energy to the output. So capacitor is discharging when switch 1 is on. And when switch 2 is on, 1 is off. When 2 is on over here, now your capacitor is charging. So it's not discharging, it's basically now is charging. So capacitor is charging, right? The saying here, switch 1 is on, capacitor discharge, switch 1 is off, switch 2 is on, capacitor is charging. So you have to take that into our consideration. So now, in an inductor, the voltage across the inductor over a period is 0. For capacitor, current through the capacitor over a period is 0. So if I use that, that means average current through the capacitor over a period is 0. Also defining that when switch 1 is on, capacitor carries IC1. When switch 2 is on, capacitor carries IC2. So if you add them together, 1 is on, 2 is on, it's one period, right? Then it's 0, that means IC1 should be equal to negative IC2, all right? And this is only possible when D is equal to 0.5, right? D is equal to 0.5. So if D is not equal to 0.5, then we have to put that D into the equation over here, all right? So now, when switch 1 is on, if you look at switch 1 is on, this is on here, right? So capacitor is discharging. So capacitor voltage is VC across it, right? And it also discharging current to the load. So load has a voltage across it, V out. So current going into the load would be V out over R. So when switch 1 is on, we're calling it I out 1 is V out 1 over R. And same with the so when switch 2 is on, we're calling it I out 2, V out 2 over R. So now let's see how current behaves when switch 1 is on. Switch 1 is on, so if you take the node over here, right? So I see that IC1 is coming to the node and I out 1 is coming to the node, so it should be equal to 0, right? There's two current. So that means I out 1 equal to negative IC1 equal to IC2 using this equation over here, right? And when switch 2 is on, and 2 is on here, I have now three currents, right? I have three currents in this node over here, right? So this current is coming IL, IC1, and sorry, IC2 and I out 2. So IC2, IL, I out 2 equal to 0. Then I out 2 equal to negative IC2, negative IL. So this is the KCL, and this is the current into the output. Now looking into the voltage, when switch 1 is on, V out 1 over here. So switch 1 is on, that means this is off here. So this is on, this one is off. And we have a voltage across capacitor VC, which is constant. So that means that's a source right now. So we have a loop here, right? We have a source over here, loop here. So voltage across this R would be the voltage divider. That means R over R plus RC times VC will give you the V out 1. It's a voltage divider. When switch 1 is off now, 2 is on, right? So look at that. This all three component here, all three of this component over here came in parallel. So V out would be what? VL over here. So V out should be equal to VL over here. And if you remember that VL is an inductor and as a storage device is still pumping current through it. So we assume that the same voltage stays here, which is basically negative V in. If we use that loop before that switching VL equal to negative V in. So that means your V out 2 equal to negative V in. So now we're doing it for 50% duty cycles. So average voltage would be 50% times switch 1 is on, 50% over here, 50% times switch 2 is on, so that if you add those two voltages, you should get average voltage. And we know V out 1, we know V out 2, we can put the back here. And also we know that IC average current to the capacitor is 0. That means VC should be equal to V out average, right? So VC is constant, so that should be VC equal to V out. There's no loss here over the period. Current is 0. There's no loss here, so VC should be equal to average V out. So that if I now put the VC equal to average V out and do the equation, that would be like this one over here. So that is when your D equal to your D is equal to 0.5. If D is not equal to 0.5, so can you develop a general equation for this circuit when D is not equal to 0.5? D could be any value from 0 to 1, right? That's for you to think about. We can discuss that in the class. All right. So now let's go to the next one here. So this is another circuit over here for you. I'm very confident that after discussing all the circuit, you should be able to find out the V out and V in relationship for this circuit for a generic value of D. And power electronic circuit is almost everywhere around you. This is one of the application for solar photovoltaic integration to the grid. This can handle almost 3,000 watt. So it has a few things here. It has first of all, it has the your converter in there, and as well as rectifier, and also this one has more than. So this is not the same. This is not the same circuit. Don't count it out. This is not the same circuit here. This is the flyback. This is the flyback regulator here. So flyback regulator is basically one of the regulator that can provide you multiple DC output. That's what we're seeing over here, multiple DC output coming out, 5 volts, 12 volts, and there's another 5 volts here. So there are the flyback, we're going to talk about that too. Flyback converter can give you multiple DC output from a single DC input. And we're going to talk about this today in the class, that how to calculate this. So we have a photovoltaic panel here. How do you integrate that into the power system, as well as how do you arrange them to maximize the efficiency? And there's some application over here. You can put all of them series. You can put them all of them in a, everyone should have their own DC converter and bring it to the common freedom inverter. And third one would be each of them should have their own inverter and converter combination. So which one is the more energy efficient? They're going to discuss that in the class. And another one is the power electronics in wind energy. So this is the front end of the wind energy. This is the back end, which is going to the grid, and in between then you can see that here there are power electronics application. We have rectifier over here, then we have boost converter here, and we have inverter over here. So different one has different application here. This is a rectifier over here. This is the buck boost over here, then boost over here, then inverter over here. So these are all power electronics application behind the blade and before the grid. So that's one of the diagram over here. You can see that you have a rectifier, inverter, grid interface, and finally it goes to the grid. And another is the electric transportation. Electric transportation, like electric car, electric semi-truck coming out now, that has the big motor to drive your wheels. So all those big motor driver, motor driver. So the motor driver is actually a very high power application of power electronic circuits. So we're going to do this practice problem in the class with you. And we have different cases to consider over here. Then we're going to see the efficiency of the converter, how to plot this one also. That's all for today for lecture 3. I'm going to see you in lecture 4.